Okay, so I want to start with the 20 questions. This is an activity we do in the classroom and it works a whole lot better. I wanted you to play with a family member or a friend just to give you some idea about what this activity is. That one partner thinks of a number, and the other partner has to ask yes or no questions to try to guess that number. And I wanted you to collect the data of how many guesses it took to guess your partner's number. So when we're in the classroom, I make a dot plot of how many guesses it did take you guys. I'm giving you just overall of what I normally find in past semesters. I did not collect the data from you guys in the last few days. And I can tell you that lots of people guess it on the 7th or 8th try. Some people get lucky and they guess it on the 4th try or the 5th try. There's always one or two very unlucky people who either take 10 guesses or 20 guesses, something like that. Maybe even more importantly, that we can't recreate through this video is I would highly encourage you to do this in your classroom. And as you do it, walk around and listen to the questions that the students are asking. Even more importantly, look at how the partner is taking the answer and are they marking off the correct things on the hundreds chart. There is so much mathematical language that can be practiced in this problem. The words at least, at most, greater than, less than. The person asking the question may not even be clear as to what the definitions are, or the person that actually has the number in their head, may not be clear, and they might actually answer the yes or no question incorrectly, so then it becomes impossible for the partner to guess the question. If you're doing younger kids, you can force them to ask certain questions. Maybe you're practicing prime numbers or multiples of 3 or even numbers, whatever. When I let Math 207 play it in the classroom, I kind of let you do whatever you want. So we get a dot plot for it. Okay, so that would have been this first one. Now, we also then have a discussion as to what are the best questions to ask. Inevitably, it does come up with that greater than or less than 50, and or asking, is it an even number? Because either one of those questions cuts it in half. Then we talk about how simply asking the 50 or less is probably better just from when you're using the 100 chart to stay organized. It's much easier to see that than the even question, because then it's going to be like every other line. But anyway, when we're in the classroom, one partner plays like you just did over the last couple days. We make this dot plot. But then when we're in the classroom, I make the other partner play differently. So after we have the discussion as to what are the best questions, and we realize the best way to play this is to cut in half every single time. So when we're in the classroom, I also tell you that these people got lucky and these people got unlucky. And what am I even basing my statement on? So the next partner I always say, I'm going to program you like a computer. You're not a human anymore. You don't get to ask whatever questions you personally want to ask. You're going to play according to a program where you have to cut it in half every single time. Sometimes that can get a bit trickier than it sounds, because if the numbers are like in between two different lines, sometimes you have to actually count in with your fingers to find that middle point to ask your next question. So then I let those partners play like a computer and we collect the data. I'm making a comparative dot plot, so this bottom line is going to be the computer, and normally I end up with results like this. Something like that. And then I sit up here and I say, well, these computers need an update because they played incorrectly. And again, why do I feel arrogant enough to make that statement? I'm going to show you in just a minute. If you play like a computer and also according to that rule that I gave you on the initial assignment, where your last guess is your number 4? And then the person says yes. You're counting that as your last guess. Then everyone should get between 7 and 8. And that's how I know these people did not play according to the exact rules of absolutely having to cut the data in half every time. And then also on your last guess, saying, is it the number 4? And the person says yes, counting that as your last guess. That's a really important distinction to make, that we were counting that. So we get a comparative dot plot. We talk about how there was probably some natural competition that you guys wanted to guess it quickly, but often people don't play as perfectly as they could until I tell them that I'm programming them like a computer. Now, where am I getting all my statements from? So, I've put this in Excel and I wanted to show you this. I think I can hold it up clearly here. So this is what we were doing, right? 100 numbers. So your first guess, you should be cutting it in half. And you'll see I kept a lucky and an unlucky column the whole time. Because as you played this game, you probably realized sometimes you couldn't cut it directly in half. Like if there's 13 numbers, that only goes to 6 and 7, right? So on your second guess, well, 50 cuts in half nicely, of course, to the 25s. But now, on the third guess, 25 does not cut in half perfectly. So I had to split it into 12 and 13. So what I was going to do is try to figure out a range of how many guesses total it should take you, right? So this first column, I'm going to keep you lucky the whole time. Meaning, if you cut 25 in half, you were lucky if you only had 12 options left. And then the unlucky, I'm going to keep you unlucky the whole time. When you cut 25 in half, I kept you at the 13. Let me get this a little bit closer. On the unlucky, when you cut the 13 in half, I kept you at 7. When you cut the 7 in half, I kept you at 4. See what I'm doing? I'm keeping you unlucky the whole time. And on the lucky, I kept you lucky the whole time. But look at what happens. Whether you did have some luck the entire time, or you weren't doing so great on the luck the entire time, you absolutely should guess it on the 7th or 8th try if you play according to how I programmed you as a computer. So this is an example of a non-linear relationship. You could graph this. It would look something like that. Oh, I didn't put the chapter up. I apologize. Let me get rid of this for a second. Part of SOLs in Virginia, and also part of your book, is to just expose and introduce your kids to non-linear relationships. Obviously, linear relationships are so much easier. So this is a great activity to introduce them to a non-linear relationship. Let me ramble a little bit more about this problem because, again, there's so many different things you can do with this. This was motivated by, I don't know when you were younger, if you ever had those handheld, battery-operated 20-question little games you could buy for like $10. Those were slightly different because you could answer yes, no, or maybe. But I was always fascinated because I would try to trick those little handheld games, and it always seemed to guess what I was thinking. So one day I tried to Google how many things were actually programmed into its memory. I probably spent an hour Googling. Of course, it depended on what company, etc., made it. But it turned out, well, before I give you the answer, let me try to again recreate what I do in the classroom. At this point, I have y'all try to brainstorm if you were allowed 20 questions, how many numbers could you have on a piece of paper that within 20 questions you actually could guess your partner's number? Like we learned here, that I can guess on the 7th or 8th guess 100 numbers, right? So if you were allowed to use all 20 guesses, how many numbers could we start with? So I let you guys sit down and think about that. Some of the answers range from 40,000 to 4 million. If you want to pause and think about that yourself, but I'm just going to kind of cut to the answer. And I'm going to show you again from my organized little Excel thing here. It's actually about 400,000 because and I set up my lucky and my unlucky column again the entire time. The idea of cutting in half, cutting in half, cutting in half, if you play like a computer, if you started with 400,000 numbers and your partner thought of one of those 400,000 numbers, you would be able to guess your partner's number on the 19th or the 20th guess. And that is really cool. And that is about what I found when I was Googling those handheld games, that I think one company actually had programmed it with 387,000 items, so close enough to 400,000. If you're doing this with younger kids, 400,000 is such a massive number that you're going to have to get creative just to get them to picture how many numbers that is. And the idea that I can actually guess it on the 19th or 20th try is really cool. And if you haven't caught this, this is really exponential decay, right? We're cutting in half, cutting in half, cutting in half. So it's the opposite of exponential growth. This is exponential decay. Looking to see if there was anything else I wanted to say on this. I think we're good there. So that one is definitely a more involved activity to do, to introduce. Maybe let me just, 20 questions is exponential decay. We're not going to worry about calculating the formula of that. We're going to go do that on something easier. You remember how we did, well, you didn't collect it, but we talked through our circumference diameter problem. We realized that is, of course, absolutely linear. It's proportional. Well, part of staying on the theme of geometry and circles, right? A equals pi r squared. You could do areas based on radiuses. You could graph those, and you would see that, of course, it's a square, parabolic. It's not linear. So that's an activity you could do in the classroom. Again, trying to incorporate geometry. Another most famous problem is the paper fold. So if you want to grab a piece of scratch paper and do this with me, you are welcome to. Or you can just watch me. Okay. Here is my scratch piece of paper. I have not folded it yet. Well, I understand that this is not a square, it's a rectangle, but go with me here. Okay. I have one piece of paper. Now I'm going to fold it in half, and really encourage your kids, if you're doing this with your kids, to fold the piece of paper in half. And then open it up, and you will have two rectangles. So I folded it once, and I have two rectangles. Okay. Now we're going to fold it again for a total of two folds, right? Have them open it back up. And you can always have them trace their folds if you want them to be able to see it better. 1, 2, 3, 4. 4 folds. And I'm going to fold it again, which would have been 3 folds total. I'm going to open it back up. And of course I have 8. You probably see where we're going with this now. You could do it again. Of course you're going to have 16. You can trust me on that one, okay? At this point, some of you guys in the classroom apparently know like what the maximum number you can fold a piece of paper is. If you're interested in that, you can go Google it. I don't remember. Apparently, of course, it might be dependent on the thickness of the paper, but that is some random tangent that doesn't have to do with this problem. But you could have the students graph this, and I would encourage you to graph it so you can visualize that this is absolutely not, maybe I should do that, not linear. Okay, I'm counting by twos over here just to make my life easy. So 0, 1, 1, 2, 3, 3, 8, 4, 4, so oops, I put him in the wrong spot. 2, 4, 6, 8. He was supposed to go here. 8, 10, 12, 14. Okay, there's my 16 mark. 0, 1, 2's going here. What have I done? 0, 1, 1, 2. I missed my 2, 4. Sorry, guys. 3, 8, 4, 16. It's much nicer, actually, if you probably show it on Excel, but definitely not linear. Be even nice if you put the 532 in there, right? So this one is probably easy enough that hopefully you can get students, particularly of a particular age, to see we're talking about powers of 2, because every single time we fold it, we are then multiplying by 2. So this is 2 to the first, 2 squared, 2 cubed, 2 to the fourth. Particularly if you put 5 and the 32 in there, that's 2 to the fifth. Sometimes students get a little confused here. This, of course, would be to the 0 power. Anything to the 0 power is, of course, 1. So you can see from here that the relationship is 2 to the x, and that is our classic exponential. So just again, introducing them and exposing them to nonlinear relationships, and chapter 13.4 covers that. Okay. All right, so that's all. I mean, something easy like this, to a power, finding the pattern when it's just to, the power is growing. I do expect you can do that. I think there's 1 or 2 homework problems. But now we're going to get back to just doing some miscellaneous book problems. I don't necessarily want to call it review because it's not supposed to be an end-all review, but usually when we're in the classroom, sometimes y'all have questions about some of the book homework, that type of thing. So some of these were problems that sometimes I get asked about, so I thought I would do it on this video. They're in no particular order. Oh, yes. Part of the handout notes for this video, I did put the 5 problems that we're going to be doing. I told you where to find it in the book, but in case you don't have the book, I think I wrote out enough of the problem. I really would encourage you to pause the video now, go do these 5 problems, then come back and watch the video for the answer key. Don't even look at the answer key in case you have practiced these. You will get so much more out of this if you practice these on your own first. Okay. All right, so now you're back. Let's see how you did. Page 290, 17b. We were supposed to do x squared divided by 2y divided by xy over 3, right? So this was to make sure that you knew when you're dividing fractions. I always call it multiply by the flip-flop. Some of you guys have a different way of remembering it, but that's what we have to do first. Multiply by the reciprocal. My board's a little crooked. Hold on. Oh, I think that's better. Okay. So this is x squared over 2y times, I just flipped it, 3 over xy. Again, it's algebra. We're just simplifying this. There are so many ways and steps you could do first if you wanted to put it all together. Of course, y times y is y squared. Well, there's 2 x's on top and 1 on the bottom. It's going to leave me 1 on top. So it should be 3x over 2y squared. You're welcome to do those rules of, 2 minus 1 for the power, and you'd end up with a 1. You can do that. Whatever it takes to get to that is the answer. This is just for you to figure out if you're okay with these problems. Okay, number 2. I think the biggest part with number 2 is a lot of times students make this problem harder than it is. So let me just get this up here so, oops, I read my handwriting wrong. I had assigned this, and I think I had said, find the linear equation. So they've given you lots of points here. If you want to make sure it's linear, how would you even check that something's linear? Take 2 different pairs of points and make sure you get the same slope. So let me say that again. If you want to check to see if a data set is linear, calculate the slope there. Calculate the slope there. If you get the same number, you have a linear line. Now, then what they did, this is almost, if you want to view that as a separate problem, once you get the equation, then you're just going to plug in the x or the y. They're using h here. It is really encouraged in the Algebra 1 classroom not to always use x and y. That h, just like y, is a function of x. So make sure you know that that's just your y. They're just using a different variable. Maybe that represents height or something like that, right? So I had already checked. I know I'm dealing with linear, so those are the 2 points. So we're just going to practice one more time, making sure you're okay with coming up with the equation given 2 points. Slope. If you do that math, you'll get 7. I'm going to use the point slope form. You're welcome to do the mx plus b and then solve for b. Y minus 4 equals slope x minus 1. Distribute the 7, then move the 4 over. Check that yourself to make sure you're okay with that. You're going to end up with 7x minus 3. I reverted back to y just because it feels more comfortable, right? But that's our h. Doesn't matter what variable you call it. So then all they're asking here is, okay, if x is 25, what is h? Just put 25 in there, and you'll be able to come up with that value. And then they said, okay, well, if y is 2454, what is x? So then you'll come up with the n. You can do that. Pause me, go do that, make sure you've done that. And so if, I don't know where I want to write, if x equals 25, you're just putting it right into there. Then you're going to have your h or your y, whatever you want to call it, to be 172. And in this problem, they're just calling it m. I think just by using the m and the n, that's why students think this is a more complicated problem than it is. So now for this guy, they gave you the 2454. We know that's 7x minus 3. If you solve for x, it's 351. And again, that's what they're saying. Hey, tell us what n is. These were just placeholders. So I think that was part of the confusion for this problem. Hopefully you are really good with coming up with the line mx plus b given 2 points. Okay. Let's go on to a word problem. Hopefully if you've done all your homework up to now, you were able to do number 3. because it has quite a few of the things we've been doing in the videos and I've been assigning. Susan, Rachel, and Steve made 6 dozen cookies and ate them all. Susan ate 25% more than Rachel. Steve ate 2 more than Susan. How many did each eat? Now, first of all, this problem has always annoyed me because they used 2 names that started with S. We can't have 2 S's, right? So I just randomly decided to make Susan U, just because there was a U in her name. I let Steve stay as S, and of course I let Rachel be R. Now you do have to know what dozen is. There's 12 in a dozen, right? They ate 6 dozen, so they ate 72. The biggest part of this that you've got to make sure you understand, Susan ate 25% more than Rachel. Susan ate 25% more than Rachel. I'm going to back this up one more time, but I'm hoping you don't need this step anymore. Rachel plus 25% of Rachel, which is 1.25 R. This is representing that 125%. We've been seeing this type of stuff for a while. This is like adding my 5% tax at the end. In the small group problems, the video that I did 6 of those, I can't remember if it was a recycling problem or something, but that we were growing by a percentage. So make sure that you know that S equals 1.25 R. It's not R plus 0.25, because that would have just been like 1/4 of one cookie. This is 25% more. Oh, I used the wrong variable, didn't I? Susan. No, I didn't. Susan ate 25. Okay, no, I'm good. Oh, but Susan. This is the part that I hated. Sorry. U is Susan. Why did they do that to us? That was just an added thing that has nothing to do with understanding algebra and mathematics, and it's already tricked me. U is Susan. Susan, 25% more. Now, Steve ate 2 more. It didn't say 2%. Literally 2 more cookies than Susan, and Susan is U. 2 more cookies than Susan. So I've got this formula, and this formula. Now, where I'm just kind of thinking ahead, I mean, again, there's definitely more than one way to solve this. U is this. I could put this right in there. So I'd have some R's. I'd have an R there, but I got an S. And if I put this in there, I still have a U. How about we put this in here and in there? Look at what happens. If I put this here, then I know Steve is now 1.25 R. I just put that right in there, plus 2. Please make sure you know this is not 3.25. This is apple and orange, right? This guy has a variable. He doesn't. Now, okay, yeah, I'm going to take this and I'm going to put it into there. So, my U, I said I wasn't going to look at U anymore because U is 1.25 R. Plus S, I said I wasn't going to look at that. I'm going to look at this. Plus, don't forget that R. That was already there. Okay. These 3 have R's in them. 1.25 R plus 1.25 R plus 1 R. 2.5, 3.5 R. That little 2 is just sitting by himself. Subtract the 2 from both sides. 3.5 R equals 70. Divide both sides by 3.5. You will get 20. And now you can stick it in here to get Susan, and then stick that in there to get Steve. So once you find that R is 20, you should definitely find that U, which we're representing as Susan, is 25. And then Steve, which we represented as S, is 27. I'm going to erase, so pause it if you So want to look at that. All right, going on to number 4. Oh, number 4 has 3 different quick little, come up with the equation of the line. I tried to pick 3 that, again, were slightly tricky and tend to give my students a little bit of a hard time. So technically this is number 4. So I need a graph parallel to this. I'm just writing the highlights right now. The whole problem is part of the notes for this video. Okay, now remember, parallel and perpendicular all have to do with the slope. Don't get tricked. The slope is not 5. The only way for you to be able to tell the slope is to get it in slope-intercept form, right? So that's the first thing you have to do on all of these. You have to get it into slope-intercept form. So 3y equals, I'm just going to move all that over, minus 5x plus 7. So y equals minus 5/3 x plus 7/3. Now I can see this is the slope, right? So I needed something parallel to that. Parallel does mean same slope, but if you go back to probably the very first video that we did for algebra, you can't use the intercept of 7/3 because then you've just written the line again, and that's not parallel. That's gosh, I just totally went blank on what I was going to say, but that's the same line. We want, my hands here, parallel lines. So, got to use the same slope, plus basically any number except for 7/3. So there's actually infinite answers to this. Put a 2, put a 10, put a negative a million. I don't care. You're allowed to use any number right here except 7/3. Because if you use 7/3, you just wrote the line again, and they're not parallel. And there's my negative. Yes, same slope. Okay. So yeah, infinite answers. That sometimes confuses students. 20D says we need a graph perpendicular to 2y minus 7x equals 4. So again, the first thing, we've got to get it in slope-intercept form, right? So 2y equals 4 plus 7x, or y equals 2 plus 7/2 x. Now I did purposely write b plus mx there because I want to make sure you know that sometimes if you're not planning it, you might have just your constant here and then the variable there. You got to make sure you don't get tricked, that you know that's the slope. Slope is whatever's connected to the x. Perpendicular says then I have to flip it and change the sign. This was positive, so I'm going to negative, and I flip it. Okay, so y equals minus 2/7 x plus any number. Again, something with infinite answers. Now, why does that make sense? Trying to figure out where I want to draw. I've lost my, here, let me get blue for a second. Think about it. If you graph this, I guess it's going to look something like that, right? There is infinite lines that are perpendicular. Oh, I'm terrible drawing. That's perpendicular, that's perpendicular, that's perpendicular, that's perpendicular, that's perpendicular. There's not just one answer that's perpendicular because it did not tell us that it went through a special line. It's just like, hey, give me a perpendicular line to my blue one. Well, there is an infinite number of answers. So any number you could put there. It's just make sure that's the most important part, that you're using the slope of -2/7. All right, what's next? I think there was another one on number 4. Yeah. This was, so I'm still on number 4, SE number 10. So we want parallel to y plus 2x equals 5, but passing through the 0.17. So we don't get to just write any old parallel line. They've given us an extra bit of criteria, right? So the first thing is to get this into mx plus b form, so I'll know what the slope is. Okay, so parallel. I know I've got to use the same slope, and it has to go through that point. This is again, I'm going to use point slope form. You can do the mx plus b. Y minus y1 equals slope x minus x1. Now I just got to clean this up. Add the 7 to both sides. Minus 2x plus 9. So this one was kind of a combination of a couple of problems. All right, one more problem. I guess I called it number 5. This is from chapter 15.2, learning exercise 18. Oh, this is just solving system of equations. I love this stuff. Because again, there are so many different ways you can do it. So I would beg you to have practiced this before you watch me. As long as you get the answer in a valid way, it does not matter if you do it my way or not. All right, well first, I really want to encourage you. None of us like fractions. Feel free to get rid of the fraction. It might help you see it better. So I'm just going to copy this over so I remember what I'm doing. Now, I know it's only out of 2, and that's a pretty easy denominator, but goodness, we're still allowed to get rid of it. Multiply each term by 2. As long as I do it by every term, I'm good, right? 2 times 3 halves. I hope you know that's 3y. Plus 2 times 3, so we got 6x. 2 times 26. Don't forget over there, that's very common to forget to multiply that by 2. I much prefer to see that. Now, you can do this as elimination method. It's probably really asking for that because you can't do it the way it's set up here. Everything has to line up, but that is a completely valid way. I'm going to do it a little bit different. I see that 6x equals that. I'm actually about to do it slightly different than my answer key. Sometimes once I do things on the second and third time, I find an even quicker way to do it. Oh, I know what 6x is. Then let me just stick that right in there. This is just a form of substitution. So I've got 3y plus y plus 40. I just substituted that in, equals 52. 3y plus y is 4y. How about we subtract the 40 from both sides? So y equals 3. Put that in wherever you want. Don't think you got the wrong answer. Even though the y was such a nice 3, once you put it back in, you're going to realize the x, it's a repeating decimal at 7.16, repeating. So that's kind of awkward because you had 43 divided by 6. I wasn't expecting that, but that is the correct answer. All right. There will be one more video after this. It's going to include 3 more of the real-life algebra problems. And then some other miscellaneous review. Hold on. Yes, because I want you to do those real-life algebra before you watch the video. So your homework. Real-life algebra, if you haven't already done them, number 2, 7, and 10. Do those before you watch the next video. I do have a helpful hint. Number 7, it's actually using the empirical rule to get you started. Okay, so just kind of keep that in mind, that it is pulling something from the empirical rule. But we will do those 3 on the next video. Always good to do them first so you can get more out of the next video. All right, see you soon.